Hi, Stu Schwartz for MasterMathMentor.com. This is video BC15b. The topic is Taylor polynomials, and it covers the BC manual pages 83 through 85. Let's go back 100 years. There are no calculators or devices to accurately determine trig functions. We have a road that borders water, but a mountain that comes down to water level blocks it. Engineers propose to bore a tunnel through the mountain, so it will come out at the exact spot as shown on the figure. At what angle theta to the waterline should they bore the tunnel? Mathematically, this is easy. Tangent theta equals 900 over 1000, which is equal to 0.9. So theta equals the inverse tangent of 0.9. But we do not have any device to calculate this. So we will create a Taylor polynomial centered at x is equal to 0 for f of x is equal to the inverse tangent of x. We start with f of x equals the inverse tangent of x, and f of 0 equals 0. F prime of x is equal to 1 over 1 plus x squared, and f prime of 0 is equal to 1. We then go to the second derivative, and we get negative 2x over 1 plus x squared quantity squared. And f double prime of 0 now equals 0. So now our derivative gets more difficult. We take a look at the third derivative and get the expression will be over 1 plus x squared quantity to the fourth, and the numerator will be 1 plus x squared squared times negative 2 plus 2x times 2 times 1 plus x squared times 2x. And the third derivative at 0 turns out to be negative 2. So the inverse tangent of x is approximately equal to x minus 2x to the third over 3 factorial, which is x minus x cubed over 3. Plugging in 0.9, we get inverse tangent of 0.9 is approximately equal to 0.9 minus 0.9 cubed over 3, which is equal to 0.657. Changing that to degrees, we multiply by 180 over pi, and we get 37.643 degrees. But is two terms enough? Taking the third derivative is not going to be easy. And suppose when plugging in 0, we get 0 again, as we did with f double prime. Then we'd have to do it again. And even then, how do you know you have enough terms so that the angle to bore the tunnel comes out within a foot of the correct location? That was an important problem for engineers of the day. As an analogy, most of you, years down the road, will retire. You will have amassed a certain amount of wealth that you hope will sustain you through the rest of your life. But how do you know how much you will need? Should you continue to work to amass more wealth? And when do you know that you have enough? This is a problem no calculator can really solve. The issue in the accuracy of our calculations in calculating an unknown variable, whether it be a Taylor polynomial or determine when to stop working, is the subject of this video. By the way, using just the third degree Taylor polynomial for inverse tangent of x would have been a disastrous mistake. We would have ended up approximately 135 feet from the correct location. The inverse tangent of x can be written as x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7, etc. And we would need to go to the 23rd Taylor polynomial approximation to get our result within 0.1 degree of the correct location. A Taylor polynomial is an approximation technique. This approximation has little value unless we have some sense of how accurate it is. As promised, we're going to get a little bit heavy into theory. If we have some function f of x and we approximate it with an nth degree Taylor polynomial, we create a remainder. For instance, if you really weigh 165 pounds, and I look at you and approximate your weight as 160 pounds, the remainder is 5 pounds, the difference between your real weight and the approximate weight. We call Rn of x the Lagrange remainder, named after the 18th century mathematician Joseph Louis Lagrange, and is the difference between the function f of x and the approximation Pn of x. So f of x is equal to Pn of x plus Rn of x. We now introduce Taylor's theorem. Taylor is Brooke Taylor, who was responsible for the Taylor polynomials. If f is differentiable through order n plus 1 in an interval I containing c, then for each x in I, there exists a z such that f of x is equal to f of c plus f prime of c times the quantity x minus c plus f double prime of c times x minus c quantity squared over 2 factorial plus f triple prime of c times x minus c to the third power over 3 factorial plus plus the nth derivative at c times x minus c to the nth power over n factorial plus Rn of x. Rn of x, the Lagrange form of the remainder, is the n plus first derivative of f at z over n plus 1 factorial times x minus c to the n plus 1 power. We also have the Lagrange error, which is the absolute value of the Lagrange remainder, or the absolute value of the difference between the function and the nth degree Taylor polynomial for f. The difference between the remainder and the error is that the Lagrange remainder can be either positive or negative, while the error is always positive. For instance, if you weighed 165 pounds and I guessed 160 pounds or 170 pounds, the error in both cases is still 5 pounds. Further, we describe the Lagrange error as the absolute value of Rn of x, which is the absolute value of the n plus first derivative of f at z over n plus 1 factorial times the quantity x minus c to the n plus first power. That gives the maximum error in using the nth degree Taylor polynomial in approximating f. I know this does not make much sense, as we are introducing all sorts of different variables, including this variable z, which seems to come out of nowhere. So we're going to take a look at an analogy first, and then we're going to do a number of examples which will make this concept clear. We explain this by analogy. Ted wants to know how far it is to Lisa's house. He gets explicit directions from his house to her development and has to make the turns as shown in the figure. He travels the 20 miles and gets to the loop. He realizes at that point he has lost her address. He knows that she lives at some house on the mile-long loop, but he does not know exactly which house is hers. So, when he reaches the loop, he is a maximum of 0.5 miles from her house. He may be closer, but the maximum distance that he would have to travel if he knew her address would be 0.5 miles. That's what the Lagrange error finds. The nth degree Taylor polynomial approximates the value of f of x at some number a. The Lagrange error gives the maximum amount that this approximation deviates from the true value of f of a. The actual error may be in fact smaller, just as when Ted reaches the loop, he may be less than 0.5 miles from Lisa's house. But the Lagrange error gives an outer bound of the error. It represents a worst case scenario. The Lagrange remainder, or Lagrange error, is dependent upon the n plus first derivative at z for the function f. There are generally two types of problems. First, when the maximum value of the n plus first derivative at z is easily determined, or when the maximum value of the n plus first derivative at z is given to you. We will look at both. Number 11 reads, find the accuracy of the third degree Maclaurin polynomial for sine of 0.1 using the Lagrange remainder. What this is asking is when we use the third degree Maclaurin polynomial for sine of 0.1, how far off might our answer be from the actual value of sine of 0.1? To solve this problem, there are a number of questions to be answered. To do so, we will generate a table, and I will highlight each row. In the first row, we are interested in the function and the third degree Maclaurin polynomial for it. Our function is f of x equals sine of x, and we have previously shown that the third degree Maclaurin polynomial is x minus x cubed over 3 factorial, which is x minus x cubed over 6. We are next interested in the third degree Maclaurin polynomial for sine of 0.1, which is p of 3 of 0.1. And that turns out to be 0.1 minus 0.1 cubed over 6. Accuracy is the name of the game here, so we will get as much accuracy from the calculator as we can. And we get 0.0998333. We next want R3, the remainder for the third degree Maclaurin polynomial. This is the fourth derivative at some value z, x to the fourth over 4 factorial. It is x to the fourth because it is a Maclaurin polynomial, and we are doing it centered at 0. To determine the value of R3 of x, we need to take a look at the fourth derivative at z of f. The function is sine of x, so the first derivative is cosine x. The second derivative is negative sine x. The third derivative is negative cosine x. And the fourth derivative is sine x. So we're right back to where we started, and the fourth derivative at z is sine z. Next is the key step. We want the maximum value of the fourth derivative at z in the interval 0 out to 0.1. So we are interested in how large the value of sine of z could be between 0 and 0.1. We are not allowed to use a calculator. If we did, we could just simply calculate the sine of 0.1. We know the sine function, the largest value of the sine function, is 1. And we want to make our calculation as easy as possible. So we will say that the maximum value of the fourth derivative at z is 1. More about this later. So we go back to our Lagrange remainder, which is R3 of x, which is the fourth derivative of f at z times x to the fourth over 4 factorial. And we know that the fourth derivative of z has a maximum value of 1. X is 0.1 raised to the fourth power over 4 factorial, which turns out to be 0.0001 over 24. So let's calculate that, and we get 0.0000041667. So our final statement is that sine of 0.1 is between P3 of 0.1 and P3 of 0.1 plus R3 of x. And therefore sine of 0.1 is between 0.0998333 and 0.0998375. You can argue that the maximum value of sine z on the interval 0 to 0.1 is sine of 0.1 based on your knowledge of the sine function. But we don't know the value of sine of 0.1. In fact, that's what we're trying to find. So we choose a convenient value for the maximum value of sine of 0.1. Again, based on our knowledge of the sine function, we know it never gets larger than 1. So it's convenient to say that the maximum value of the fourth derivative at some value z is 1. As an analogy, if you go out to an expensive restaurant where you never ate, you might bring $100, figuring that there's no way that it will ever cost that much. There might be a lesser amount that you can take, and you'd be safe as well, but $100 is just convenient. So remember that this was all discovered in the 1700s before there was any technology available. So to keep the computations as easy as possible, this maximum value of the fourth derivative of z is kept as simple as possible. Number 12 reads, using the fourth degree Maclaurin polynomial and Lagrange remainder for f of x equals e to the x, find the largest possible value for 1 over the square root of e. Like the last problem, we will do this by completing a chart. Our function is f of x equals e to the x, and we wish to create the fourth degree Maclaurin polynomial. That is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. We developed that in video 15a. This will be one of the Taylor polynomials you are required to memorize. Since we are looking to calculate 1 over the square root of e, that is e to the negative 1/2. So we want the value of the fourth degree Taylor polynomial at negative 0.5. And that is 1 minus 0.5 plus negative 0.5 squared over 2 factorial plus negative 0.5 cubed over 3 factorial plus negative 0.5 to the fourth over 4 factorial. And that gives 0.606770833. So the remainder for the fourth degree Taylor polynomial is the fifth derivative of f at z, x to the fifth, all over 5 factorial. The fifth derivative of e to the x is still e to the x, so the fifth derivative at z is e to the z. We want the maximum value of e to the z on the interval negative 0.5 to 0. E to the x is an increasing function, so its maximum value must occur at e to the 0, which is 1. So like the last problem, our fifth derivative of z is 1, and we multiply that by negative 0.5 raised to the fifth over 5 factorial, which is negative 0.03125 over 120. Calculating that, we get negative 0.000260467. Since this number is negative, we can say that 1 over the square root of e is between p4 of negative 0.5 plus r4 of x, and has to be less than p4 of negative 0.5. So 1 over the square root of e has to be between 0.6065104.167 and 6.606770833. So the largest possible value we would get is 0.606770833. Let f of x be a function given by cosine of 2x plus pi over 6, and let p of x be the third degree Taylor polynomial for f about x equals 0. We want to show that the Lagrange error bound for f of 1/3 is less than 1/100th. The Lagrange error bound is the absolute value of R3 of 1/3, which is the absolute value of the fourth derivative of f at z over 4 factorial times 1/3 to the fourth power. So we have to take a series of derivatives. The first derivative is negative 2 sine of 2x plus pi over 6. The second derivative is negative 4 cosine of 2x plus pi over 6. The third derivative is 8 sine of 2x plus pi over 6. And the fourth derivative is 16 cosine of 2x plus pi over 6. To find the maximum value of 16 cosine of 2z plus pi over 6 on the interval 0 to 1/3, we can think of it as two ways. First of all, we know that cosine is a decreasing function starting at x is equal to 0. So when z equals 0, we will have a maximum value, and that will be the 16 cosine of pi over 6, which is 16 square root of 3 over 2, or 8 square root of 3. If you want to be a little bit more conservative, you can say that the cosine function has a maximum value of 1, like we did with the sine problem several problems back. And we can say that we will get the maximum value will be 16 times 1 is equal to 16. So depending upon which way we look at it, the Lagrange error will be 8 square root of 3 over 4 factorial times 1/3 to the fourth, the absolute value of that, which is the square root of 3 over 243, which is equal to 0.007, and that is less than 1/100th. If you look at the conservative approach, you will get 16 over 4 factorial, or times 1/3 to the fourth, and the absolute value of that is 0.008, and that is also less than 1/100th. There is no one right answer for the Lagrange error bound. Again, it's similar to the analogy we made with the restaurant. You can bring a lot of money to the restaurant and you are sure that no matter what you order, you can pay the bill. But there are lesser amounts that you can bring and still be able to pay the bill. That is what's going on here. 14 reads, let f be a function having derivatives for all orders at all real numbers. The third degree Taylor polynomial for f about x equals negative 2 is given by p of 3 of x is equal to 9 minus 4 quantity x plus 2 plus 5/3 quantity x plus 2 quantity squared minus 20 over 7 x plus 2 quantity cubed. The fourth derivative for f satisfies the inequality that the absolute value of the fourth derivative of x is less than or equal to 25 for all x in the interval negative 2 to 0. Find the Lagrange error bound for the third degree Taylor polynomial approximation to f of negative 1.6 and the range of all possible values for f of negative 1.6. This problem appears difficult, but in reality it is quite easy. You are given the largest value of the absolute value of the fourth derivative of f on the interval negative 2 to 0, and that is 25. So we can immediately write the Lagrange error bound for the third degree Taylor polynomial to be 25 over 4 factorial times the quantity negative 1.6 plus 2 raised to the fourth power. And that is 25 over 24 times 0.4 to the fourth power. That will be positive, and we get 0.02667. Next, we find the third degree Taylor polynomial for f at x equals negative 1.6, and we get 9 minus 4 times 0.4 plus 5/3 times 0.4 squared minus 20 over 7 times 0.4 raised to the third power. And that is 7.4838095524. So f of negative 1.6 must be between that value minus 0.02667 and the Taylor polynomial approximation plus the Lagrange error bound, which is 0.02667. And that means f of negative 1.6 is greater than or equal to 7.457139524 and less than 7.510479524. The reason that we do this is that we are not sure whether the Lagrange remainder is positive or negative. All you were given was the absolute value of the fourth derivative of x at being less than or equal to 25. So that is why we have to subtract the Lagrange remainder or add the Lagrange remainder. (15) reads, let f be a function having derivatives for all orders of real numbers. Selected values of f and its first three derivatives are given in the table to the right. The third derivative is decreasing on the interval. X is greater than or equal to negative 1 and less than or equal to 1. Use the Lagrange error bound to show that the second degree Maclaurin polynomial approximates f of 0.2 with error less than 0.01. This is one of those problems where a lot of information is given to you, but most of it is irrelevant. The Lagrange error for the second degree Maclaurin polynomial will be the maximum value of the third derivative of f at z over 3 factorial times 0.2 raised to the third power. Since f triple prime is decreasing on the interval negative 1 to 1, the maximum value of the absolute value of f triple prime of x, where x runs from 0 to 1, is 4. So the Lagrange error, f triple prime of z over 3 factorial times 0.2 raised to the third, is 4 over 6 times 1/125th. And that is equal to 0.005333, etc. And that is less than 0.01. To give you a sense of where we're going, suppose you were asked to find the value of 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus, and this pattern goes on forever. What is its value? Perhaps you think the expression 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc. can be written as the quantity 1 minus 1 plus the quantity 1 minus 1 plus the quantity 1 minus 1 plus etc. And that would equal 0 plus 0 plus 0 plus dot dot dot, and we would get an answer of 0. But maybe you thought the expression 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus dot 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 can be written as 1 minus the quantity 1 minus 1 minus the quantity 1 minus 1 minus the quantity 1 minus 1, etc. And then it would be equal to 1 minus 0 minus 0 minus 0 minus dot dot dot, and our answer would be 1. Both answers seem to be correct. There is no mistake in the logic, and yet they both cannot be correct. If they were, then 0 would equal 1, which we know is not true. Welcome to the world of infinite series. That will be the topic of all future videos.